This program is brought to you by Stanford on iTunes U at Stanford University. Please visit us at itunes.stanford.edu.
What I want to talk, what we were talking about last time was the density matrix description of probabilities. Now, the density matrix is another way of speaking about the probability postulate, and it's a situation which is more general than knowing the state vector of a system. It's roughly speaking when a system has been prepared, but you don't know how it's been prepared, and so it may very well have been prepared in a very definite state of some sort. I gave you an example last time where an electron spin might be prepared along a direction by placing the electron in a strong magnetic field, but somebody else did the preparing and didn't tell you what direction the magnetic field was in. Perhaps they gave you a probability distribution for different directions of the magnetic field. Thank you for the coffee tonight. I really need it. I hope this is coffee. So it's a situation where the system has been prepared, but you simply don't know how it was prepared. Then how do you describe it? There has to be some description. You may have some degree of knowledge about how it was prepared. You may have none. Incidentally, if you have none, if you have no knowledge at all, then the density matrix has all equal eigenvalues. It's proportional to the unit matrix, and each eigenvalue is 1 over n, where n is the total number of states, and that just means complete random information you simply don't know. All the possibilities are equally weighted. But let's just go back and discuss a little bit more, to review the basic equations and the basic concepts that go with the density matrix. The density matrix is the analog of knowing the probability distribution for classical states. Classical states have some probability distribution. In many contexts, you would call it a probability density, a density in phase space, or a density in coordinate space, a density of probability. That's where the word density matrix came from, and it's basically a quantum analog of the notion of a probability density or a probability distribution. The condition that the sum of probabilities adds up to 1 is denoted by saying the trace of the density matrix is equal to 1. Remember, the trace is the sum of the eigenvalues. The eigenvalues themselves of the density matrix can be thought of as the probabilities for different states. So first of all, the trace of the density matrix is equal to 1. The density matrix itself is a Hermitian operator. That's basically just a condition that the probabilities are real. Probabilities are real, so in classical physics you would assign real probabilities. Only somebody with a very bad disorder would assign them complex probabilities. Wouldn't make any sense. The analog of that for quantum mechanics is that the eigenvalues of the density matrix are equal to 1. The eigenvalues of the density matrix are real. Let's label them lambda I, where I is equal to I equals 1, 2, dot, 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 up to n, where n is the number of dimensions of the vector space.
Are they all positive, too?
And they're all positive. Good. And they're all positive. Right. Each eigenvalue goes with some eigenstate. Right? And in some basis, some particular basis in the space of states, some orthonormal basis of states, corresponds to the eigenvectors. Incidentally, remember that the eigenvectors of a Hermitian operator are all orthogonal to each other, so they form a basis. So there's some basis in the space of states, which is just n mutually orthogonal vectors, each one of them being an eigenvector and each one having an eigenvalue lambda sub I, you can simply think of the lambda sub i's as the probabilities that the system was prepared in the ith eigenvector of the density matrix. If all the eigenvalues are equal, it effectively means you know nothing. You don't know what state the system is in. The density matrix then is proportional to the unit matrix, all the same eigenvalues, each eigenvalue being 1 over n. That's one limit. That's the limit of complete ignorance. The limit of maximal knowledge is a pure state. That means that you know what state the system has been created in. Right? In that case, we can say the system is described by some pure state. I won't tell you which one, but we assume we know which one. Some pure state psi. And when the system is described by a pure state, there's still a density matrix. You can still introduce a density matrix. And the density matrix is simply the projection onto that pure state, the projection operator that projects onto that pure state. Right. It's written this way. So if there's only one state, and you know which it is, it has probability 1 for being in that state, then the density matrix is just psi.
So how do I express that the state could be this one with half of probability and the other half being some state 45 degrees to it?
Oh, no, that's not a good concept. The density matrix, being a Hermitian operator, has a set of mutually orthogonal eigenvectors. And it only makes sense to discuss the probability for which state it's in that basis. And so the only situation you would talk about. Now, we can answer the question, let me come back to it, where you don't know how the system was prepared. Somebody may have put the magnetic field this way, or may have put it at 45 degrees. We can figure that out. We'll figure that out later. I'll come back to it. But still, it will be the case that the density matrix always has mutually orthogonal eigenvalues. So I will take up that case either now or next time.
You mentioned pure state. Can you differentiate pure state from mixed state?
A mixed state means a density matrix which simply has more than one non-zero eigenvalue. Yeah. And that's what it means. Okay, in German it's called a Gemisch. It's the word I learned when I was a young student, because German was still one of the important languages of physics. Now it's just called a mixed state, I think even by Germans. Any Germans? I'm just curious whether in Germany they call a mixed state a mixed state. I actually don't know. Gemisch was the word that was invented by the fathers of quantum mechanics.
It's a good German word.
What's that?
It's a good German word, Gemisch.
Gemisch, yeah. Okay. Now, what are the, yes, let's just point out one thing. Take this matrix here, or take this operator. It obviously has a single eigenvector with eigenvalue 1. What is the eigenvector of this matrix with eigenvalue 1? It's just psi, the same vector. If I take this and operate on it, let's assume that now psi is normalized. I assume that it's normalized. If I apply this to psi, then psi is equal to 1. It just gives me back psi. So in fact, psi is an eigenvector with eigenvalue 1. Any other state orthogonal to psi, let's take some other state which is orthogonal to psi. We call it phi. If it's orthogonal to psi, then you get 0. So if the density matrix is a simple projection operator onto one particular state, then it has one non-zero eigenvalue. The density matrix is representing a pure state, and the pure state is just psi. Now, whether or not the state is pure or mixed, the rule for average values, they're usually called, even in this case, expectation values. I didn't want to confuse the terminology, confuse the notation, so I just indicated an average value. Let's say the average value of the observable M, which I'll indicate by putting a bar over the top, is just the trace. I'll remind you in a moment what the trace is. The trace of the density matrix times M. And incidentally, it's not hard to prove that a trace of a product of two matrices, whether or not the matrices commute, whether or not the trace doesn't matter which order you put the operators. So you can also write trace of M times rho, and it will make no difference. That's the average. And definition of the trace, let me remind you the definition of the trace of a matrix. You take any base, excuse me, you take any basis whatever. The trace has the property that it doesn't matter which basis you calculate it in. It's an invariant on the changes of basis of the vector space. All right, but in any case, we take some basis. It doesn't have to be the basis in which rho is diagonal. It can be the basis in which the rho is diagonal. But even if it's not diagonal in this basis, nevertheless, the trace is defined as I rho m, whatever the matrix in question is, times I summed over I. Okay, in other words, you just take the ith matrix element of the operator in question, and you sum it over all I. That's the definition of the trace. And let's work it out just for the very simple case in which rho is a projection operator. In that case, M is equal trace. I'll write the trace in a moment. Psi M. And now we take a complete basis, whether or not, as I said, it does not matter whether the basis is the basis in which rho is diagonal. I. All right, so now we have to do a little bit of gymnastics. Oh, this is summed over I. If I forget to write sum over I, remind me. It's almost always the case that when you have an index like I repeated twice, almost in every equation I will ever write down, it's implicit, or maybe I'll try to make it explicit. If I forget, remind me. But it's almost always the case that it will be summed over, so that I is really just a summation index. You can call it J if you like, it doesn't matter. All right, let's check this out. Let's see if this makes sense. We can rewrite this by just shifting this factor over to this side. Let me do it. All right, let's rewrite it. I psi m I psi. Now you have to remember the rule. Whenever you see I and I back to back like this, summed over, that's the unit matrix. That's the unit operator. The sum of I is the unit matrix. It can always be canceled out. It's just the unit matrix. It makes no difference. You can just remove it, and the result is that it's psi m psi. Well, that's not too surprising. The average of m is the expectation value of m if you have a pure state. Now, supposing you don't have a pure state, let's suppose we don't have a pure, question?
Should that be M bar?
Yeah, this. No, sorry, M bar up here, yes, thank you. Very good. Yep. Okay, let's take the more general case when we don't have a pure state, and see what we get. But let's evaluate it. Let's see. Yeah. Okay, so again, we have to take trace of rho m. But let's do the calculation in the basis in which rho is diagonal. All right, so to calculate the trace, we put I rho m I summed over I. I'm not going to write a summation sign. I'll suppress the summation sign for now. Just summed over I. But now we can insert a complete set of states between rho and m. This is a trick we constantly keep doing in order to reduce the calculation to something involving matrix elements of both rho and m. We stick in between there a complete set of states, and we write it in the form I. Maybe, I guess I'll put the sum. Sum on I, rho, m, but I'm going to insert in here a sum over j. And now it's a sum over both I and j. Now, if I'm working in the basis in which rho is diagonal, then I know what the matrix element I rho j is. This is just these I rho j. What is that? That's just the matrix. Has an I index and a j index. The row or the column, let's see, which one is which? This one is whichever. Yeah. J is the column, I think. Yeah, right. Okay, but since rho is diagonal, this object here only has a matrix element if I is equal to j, and then the matrix element is just lambda j, the eigenvalue. So the sum over I and j becomes a sum only over one of them, and let's take it to be j, because I has to equal j, because rho is diagonal. And then we have j, m, j. I've put j here because I has to equal j in the sum. Well, what is this? This is just the expectation value of m in the jth state. This is just the probability of the jth state. So this reads exactly what you might expect. It's the average of m in the jth state weighed with the probability, which is the probability of the jth state. Okay. So you can think of the eigenvalues of rho as the probabilities to be in the jth state, but only in the basis in which rho is diagonal. Yeah?
Is that really j and j instead of j and I there?
Yes, because I has to be equal to j, otherwise you don't get anything. Right. So for trivial reasons it is.
You are still summing over I, right?
You're still summing over j here, over j. Right. Yeah, here I really broke my own rule. This thing is repeated 3 times. Right. Okay, those are the rules about density matrices. Let me remind you of one more definition. If you're given a probability distribution, probabilities, let's say p sub I, this is classical probabilities now, p sub I, the ith probability for the ith possibility, then the entropy is defined S for entropy. I don't know why they chose S. Why it's not E, probably E because it would get confused with energy. S for entropy is equal by definition. This is the definition of it, but we can say what it means roughly. It's again the sum over all of the possible configurations or all of the possible possibilities of minus p sub I times logarithm of p sub I. That's its definition. Again, if only one of the p's is non-zero, then it's got to be 1. All right? Logarithm of 1 is 0. On the other hand, all the other p's are 0. So in that case, if you have complete knowledge, then the entropy is 0. So 0 entropy means complete knowledge. You know precisely that the probability distribution is peaked at one particular point, 0 everywhere else. The other extreme is when you have complete ignorance. And in that case, each p sub I is 1 over n. Let's take it to be the same n here. Each p sub I is 1 over n, and then you get s is equal to, before you do the sum, 1 over n log 1 over n, but it's minus log 1 over n, so that's actually the same as log of n. But then you have n terms in the sum, so you have to multiply this by n, and the answer is that the entropy is logarithm of the number of states. The entropy is, roughly speaking, the logarithm of the number of states which are important in the probability distribution. That's as close as I can get to give you a definition in words, but you don't need a definition in words. This is precisely what it is. But nevertheless, it is true that if you have a probability distribution which has fairly large over some set of states and then pretty damn small everywhere else, that the answer for the entropy will essentially be logarithm of the number of states for which the probability distribution is significant. So it's a measure of the degree of ignorance. The more ignorance, in other words, the more states that the probability distribution is spread out over, the less you know about the system. The more you know about the system, the fewer the states, and the smaller the entropy. Okay, so it's measure of ignorance, or a measure of, well, yeah, that's... All right, now we want to come to entanglement. Entanglement happens when we have more than one system. So let's suppose we have a system composed of 2 parts. And let's suppose we have some basis, and the basis is labeled by a state or an observable A for one of the subsystems and B for the other. Now, for the case of 2 spins, A and B could be would both be up and down. We can have up, 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 down, down, up, down, down. Okay. Other possibilities, we could have a spin with 2 states and an atom with 4 states or 3 states. Okay, in that case, A would go from 1 to 2 or up and down. B would run over 1 to 3 or 1 to 4. And so altogether, the total number of states would be the product of the number of configurations of the subsystem A times the number of subsystem B. So if we had a spin which could be in one of 2 directions, and we were putting it together with an atom which could be in 3 possible states, the total number of states would be 6, but it would just be 3 times 2. Okay. Let's say that little a runs from 1 to capital N, and little b runs from 1 to little n. They don't have to be the same. They could be 2 quite different systems. Okay. Then the most general state of the combined system that we can write is a sum. And we're going to sum over A and B of some set of coefficients called a wave function of A and B, function of A and B. Now, A and B are discrete, or at least for us now, A and B are discrete variables. In a more general context, A and B might even be continuous, but for our studies here, where we're studying qubits and discrete systems, A and B run over integers. They're integer-valued variables, but we can still write psi of A and B, sticking in any pair of integers. That gives us a complex number, multiplied by the state vector AB, summed over A and B. That's the most general state we can write down. If we want to normalize it, which I do, then we want the sum over A and B of psi star psi to add up to 1. Okay, so I won't write that down. The sum over A and B of psi star times psi should be equal to 1, and that's our normalization condition. Okay, let's now suppose that we're doing an experiment which does not involve B. It could be because the two systems are separated from each other, and Bob is down at that end of the room. He doesn't even bother looking at his system at all. Alice is up at this end, and Alice is going to do an experiment, and the experiment is going to involve only the A degrees of freedom. Okay. The observable that she's going to measure, let's call it M. M is an observable for subsystem A. That means mathematically that when M acts on a state vector AB, it may act on the A coordinate, but it will just leave the B coordinate alone. We've done this before. We've done this with spins. So M effectively is only a matrix in the A system here. It acts on the A degree of freedom and leaves B alone. It doesn't touch B. So whatever it does to a state vector, B is completely passive and doesn't change. The matrix may act on the A coordinate, and that's all. So that's a degree, or a variable, sorry, an observable that's associated with the A subsystem. And let's calculate the expectation value of it in the state for the combined system. So what do we have to do? We have to take, first of all, we have to take the bra vector associated with this. Let's construct or rewrite it as the bra vector. Sum over A and B, psi star, well, let's see, we're going to need two sets of variables. We're going to need primed variables and unprimed variables. So let's see how I did this. Yeah. Psi star of A prime and B prime, A prime, B prime, summed over A prime and B prime. This is the bra vector. Now we're going to multiply that by M, and now the ket vector, which looks exactly the same, except we won't have a complex conjugate. Psi of A and B, AB. I'll tell you what, let's take the psi and stick it on the outside here. Now we separately have to sum over A prime and B prime to define the bra vector, and A and B, we also have to sum over A and B to define the ket vector. And that's the expectation value that we're interested in. But now let's look at this matrix M. M does nothing to B, but it's a matrix as far as A goes. What does that mean? That means that B prime has to equal B. Okay, B prime and B, the operator M does nothing to B. It leaves it alone. And if it leaves it alone, then B prime and B must be the same. Okay, because...
Can I ask a question?
Yeah.
Primes on some of these variables. I mean, above you didn't use I prime and I. It's always been...
There I used I and J.
No, but for the expectation of rho m, it's I, rho m I.
No, okay. Well, we're not dealing at the moment with density matrices. We're dealing with state vectors. So let's go back and write an expectation value for a state vector. Okay? Supposing we have a wave function psi of A times A, single system. And now we want to calculate the expectation. And this is, of course, sum over A. then the expectation value is m, and now we have to write the bra vector. That's sum over a prime of psi of a prime. I know you do. A prime. Okay, so in calculating the expectation value, if the vectors on either side are expressed as sums, you have a double sum to do. And in this case, and I've called the left part of the double sum prime and the right part unprimed. Okay, so it's the same thing except we have two labels here. But now, the definition of the idea that M is an operator that acts on the A subsystem and which is passive for the B subsystem is simply the statement that the matrix is diagonal in the B's. That B on this side and B prime have to be the same, otherwise the matrix vanishes. In that case, this sum over B and B prime becomes a sum only over one of them. All right. So let me show you what the right idea is now. B and B prime have to be the same, and M is really just a matrix in the A space. It's a matrix with matrix elements A and A prime. I think I want to write them this way. All right, this is a matrix involving two variables A and A prime, but B has to equal B prime, and there's no dependence on B whatever. No dependence on B, and B has to equal B prime. Okay, so that's this matrix here. And all we have to do is remember the instruction in the rest of the expression here that B has to equal B prime. So let's do that. Psi star of A prime B, psi of AB. All right. Notice on the left we have psi star of A prime, psi of A. But as far as B goes, B, whoops. B hasn't changed. B is just passive. This is now let's go a little step further. This is still summed over B. It's also summed over A prime and A. But I want to ignore for the moment the sum over A prime and A and realize that this is a sum over B. It's also a sum over A prime and A. But let's do that later. All right? All right. Now let me group the two things that depend on B. Let me group them together. So what I'm going to do is erase this over here, and I'm going to put it back right back here. Psi star of A prime and B. All right, now imagine holding A and A prime fixed and just summing over B. That gives you some expression here. That expression no longer involves B because B has been summed over. Once B is summed over, it doesn't depend on B. Let's give this a name. What shall I call this? Psi of AB and psi star of A prime B. It's a function only of A and A prime. Is there a name for it?
Phi of A.
No.
Phi of A.
No. Try again. It's not the A and the A prime that I don't like. It's the phi. Come on, give me the right letter. Rho. Rho. This expression is in components, written in terms of matrix elements, is the trace of the product of M times rho. All right? Why is it the trace? It's the trace because I'm summing over A prime, but it's the product because I'm summing over A. This is the formula if I had arbitrary things here, let's say A double prime, then this would correspond to the A double prime, A prime matrix element of M times rho. This is the way you multiply matrices in terms of components. This expression is a trace of M times rho. Let's check that. Let's do it by longhand calculation that really is the trace. Now we're talking about a system. We're only talking about the A system now. We've eliminated the B system. We've summed over it. It's no longer even in this expression. This might have been something that made sense for just a pure A system without any reference to B at all. What would it correspond to? So let's forget B. It's passive, it's gone, we finished with it. And this is some expression only involving the A degrees of freedom. All right? I assert that it's the trace of the matrix M. Now remember, M really only depends on A and A prime. B is completely passive. B prime has to equal B, and otherwise it just doesn't depend on B. So
The identity on B.
M is the identity on B. Yeah. Yeah, right. Acting on B, it does nothing. Right. Okay, so let's just calculate trace of M. We can write it as A prime M rho A prime, summed over A prime. All of this is summed over A and A prime. A and A prime. Okay, back we have to sum it. All right, this is the trace. This is the definition of the trace. But now if I insert a complete set of states in here, it becomes sum over A and A prime of A prime M A rho A prime. That's just this. M A prime A, that's this, and rho A prime, that's this. All right, so look what we found. We found that by ignoring B, just ignoring it, and asking what are the rules when a system is a combined system with a unique state vector, a pure vector, it's a pure state for the combined system. Nevertheless, when you focus only on the A subsystem, it's described by a density matrix. That density matrix, how do you get the density matrix? You get the density matrix by taking the full wave function, letting A and A prime run freely, not summing over them, but summing over B. That eliminates B out of the expression, and it just becomes a matrix between A and A prime. So when you have a combined composite system, Schrodinger's cat and the gun, all right? The Schrodinger's cat and the gun may themselves be described by a single state vector in which they're entangled, but if we just look at the cat alone, the cat is described by a density matrix. It's described by a density matrix, and in general, that density matrix will be a density matrix of a mixed state in general. There's a very special circumstance under which it will be a pure state that will describe the A system, and I'll tell you in a moment what it is. In fact, I suppose I should tell you right now. Any questions up till now? Yeah.
Isn't tracing rho just trace of M?
Why?
Trace of M rho is the trace of M times trace of rho, and trace of rho is
Wait, trace of, no, sorry, trace of product is not the product of traces.
no.
It'd be nice if it were, make things easy, but it's not true. Trace of a product is not the product of the traces, yeah.
You said you started with a pure state, which was just AB.
No. Psi, no, not AB, but sum over AB of psi A.
Okay, so you're not dealing with, this is the most general case that you could.
This is the most general pure state of the combined system. Okay, so let me say it again. You have a combined system. It's in the purest possible state, psi. When you look at a subsystem, the subsystem will be in a mixed state, in a statistical state. Now, there's no analog of this for a classical system. If I have what would correspond to a pure state for a classical system, for a classical system, the idea of a pure state would be a probability distribution which has only one point that it's non-zero. In other words, a definite piece of information about which state you're in. That's the analog of the pure state. In other words, complete knowledge. If you have complete knowledge about the combined system, you have complete knowledge about either of the subsystems in classical physics. So in classical physics, complete knowledge about a combined system is equal, it's not equal to, but it implies complete knowledge about either of the subsystems. That's different in quantum mechanics. In quantum mechanics, you may have complete knowledge about the combined system, and yet the subsystem by itself must be described by a density matrix. Now, you say, might it be that that density matrix is special and that it corresponds to a pure state? Not in general, and I'll show you some examples. I'll show you some examples that we're already familiar with. We'll work out the density matrix for some familiar example. But let me just say, yeah.
How different is this from in classical mechanics where you have velocity distribution functions which you integrate over to get densities? So in a way you integrate it over the B state to get a density matrix, right?
Yes.
So I can think of a velocity distribution function. If you integrate it over, you get the density.
How do I get a density by integrating over? Oh, you mean if you have a combined velocity and position?
In a classical probability distribution function like the Boltzmann.
You have a combined velocity and position distribution, and you integrate. It's similar. It's similar. But the difference is that if you had complete knowledge, in that case, the velocity and the position would just correspond to two subsystems. They're not really two subsystems, but you could think of them as two different systems, two different coordinates okay. In that case, if you had complete knowledge about the system, it would mean you knew both the velocity and the position. And there's no problem with knowing the velocity and the position. And so not only would the combined system be in a pure state, but if you just looked at positions, you would have definite knowledge of position and definite knowledge of, what's that other thing called? Velocity. Yeah. Okay, so that's the difference, that there are pure states of the combined system which cannot be thought of as pure states of the subsystems. Okay, let me just tell you what is the condition. All right, so here's an interesting condition. What is the condition on psi of A and B that the individual subsystems actually are in pure states? Is there a situation or a wave function psi of A and B in which the two individual subsystems are in a pure state? The answer is yes. Any time that the wave function factorizes into a product of A, a product of a function of A, and a product of a function of B. Let's just analyze that situation a little bit and see what it says. That's a special case. Not all functions of two variables are products of functions of one variable times a function of another variable. But it's only when the wave function is a product that each individual subsystem is itself in a pure state. Okay, let's look at that a little more carefully. Let's suppose that psi of A and B happen to be equal to a product of a function of A and another function of B, and I'm going to call the other function chi of B. Really, all this is saying is that the combined system is a pure state phi for the A subsystem and a pure state chi for the B subsystem. We'll assume that phi and chi are normalized, so that chi star chi when summed over B is equal to 1, phi star phi when summed over A is equal to 1. Those conditions are equivalent to the normalization of psi itself.
So phi of A, that's composed solely of the A kets.
Well, it's not, functions aren't composed of kets, but yes, and that's right.
Well,
yeah, I know what you're.
The state itself is a linear combination of all of the A kets.
Yeah, that's right. That's right. It's a product state. Right. Right. It's a product state. Okay. So if phi happens to factorize like that, then let's calculate the density matrix itself. The density matrix for the A subsystem. Right? For the A subsystem, we have to multiply psi of A and B times psi star. You know something? I think I actually have something backward. No, that's all right. Okay. So we have to take psi of A and B times psi star of A and B. That's phi of A chi of B times phi star of A prime. We have A and A prime, but B goes with B, times chi of B, chi star of B. Summed over B. That's the density matrix rho A prime. Right. Same formula, except I've substituted for psi the product. All right, now this is very easy. The only thing that's summed over is chi. A isn't even in the sum. You can pull the phi's outside the summation, since the summation doesn't involve A altogether, and it just becomes equal to phi of A, phi star of A, times sum on B of chi of B times chi star of B. But what is that? Sum on B chi star, that's just 1. That's the normalization of chi of B. So this is all just 1. So the density matrix for a product is very simple. It's just the product of wave functions phi of A times phi star of A. Let's calculate now, in this case, the expectation value of M. It's just equal, where is it? M of A prime and A. Sorry, I missed a prime here somewhere. Right. Right. It's M of A prime and A, phi of A, and let me put phi star of A prime over here. Well, this is nothing but, written in components, this is nothing but phi M phi. In other words, the expectation value of M, and not just M, but any observable that involves only A, is exactly the same as if the state vector were just phi. The A degrees of freedom are completely and entirely described by the pure state phi. So when the wave function is a product of two factors, each subsystem is itself in a pure state, and the pure state is just either phi of A or chi of B. That's the special case when the combined system is in a pure state and each subsystem is in a pure state. But that's hardly general. Not at all general. Not every function of two variables is a product of functions of one variable. Okay. Incidentally, in this case, the density matrix, well, here is the density matrix. The density matrix has one and only one non-zero eigenvector. It's phi itself. All the other eigenvalues are equal to 0, and the entropy is equal to 0. Only eigenvalues are 1, and all the others are 0. So that's the case. That's one way of diagnosing how pure a state vector is, or how well the wave function resembles a product, is to calculate the entropy. If the entropy is small, it means you're near the situation of a pure of a product. If the entropy is large, somewhere near the maximum logarithm of n, that means you're deeply entangled. And deeply entangled means you're far from a product. Far from a product, wave function just doesn't factorize. Let's work out one particular example. Maybe we can work out some more than one particular example, but let's do at least one example of a familiar thing that we've already studied. Calculate the density matrix and calculate the the entropy. We should do two. We should make one be a, yeah, we're going to do two different examples. The first example is not going to be a pure state. The first example is going to be our friend, the singlet state, the highly entangled singlet state of 2 electrons. Okay, so what is it? It's by definition up, down, minus down, up, divided by square root of 2, right? But let's write that in terms of a wave function of 2 variables. All right. Psi has 2 entries. The first entry represents spin number 1. The second entry represents spin number 2. And here are the values that psi has. Psi up is equal to 0. I don't see up here. Do you? No. Okay. What about psi up down? That's the coefficient of this one. It's equal to 1 over square root of 2. How about psi down up? Minus 1 over square root of 2. And psi down is 0. Okay, let's calculate the density matrix for the A system now being spin number 1. So what do we have to do? We have to write down, where is it? This is the density matrix right here. Did I write it somewhere? Yeah, it's over here. This is the density matrix summed over B. Summed over B. All right, so we begin by writing down a psi next to a psi star. Let's work it down. Let's do the elements. Rho, up. Remember, rho is a matrix, but it's a matrix just in the space of 1 spin. So let's calculate its up matrix element. Its up matrix element we get by writing psi up. Let's write it again, psi up plus, this doesn't make sense yet. It will in a moment. Okay. All right, now remember we sum over the B coordinate. So let's put up, down. No, this is up. We're calculating the up matrix element. All right, let's come back to here. We're calculating the A prime matrix element. So in one place we put a psi with an A, in the other place we put a psi star with an A prime. This should be star. In this case, both A and A prime are up. So we have a psi of A and a psi star of A and a psi star of A, but we have to sum over B. So B is up, and down. That's the instruction. It's psi star psi, with the A's being evaluated as matrix elements of the density matrix and the B's being summed over. Up plus down. Okay, that's the up matrix element. Let's see what it is. Psi up is 0. So this is 0. But psi up down is 1 over square root of 2. So this is just 1/2. All right, what about rho down? For rho down, you do exactly the same thing. Psi down, psi star down, plus, same thing, psi down, psi star down. But then you fill in up, down. Do I have this right? Yeah. Okay. What is psi down up? That's minus 1 over square root of 2. It's squared. So again, we get 1/2. And down is 0, and down is 0. So this is again 1/2. Neat. What about psi up, rho up down? The matrix element of the density matrix, the up-down matrix element. Do the same thing. Psi up, psi star down, up, down, plus, write it again, psi up, psi star down, but then fill in up, up, and down, down. Okay, what's that? 0. Psi up, up is 0, and psi down, down is equal to 0. So that's 0. And of course, the other one is also 0. Rho down, up is also equal to 0. So in this case, the density matrix is just equal to rho is equal to a half, a half. It's proportional to the unit matrix. It has equal entries. Those entries can be thought of as probabilities if you like, but its trace is 1. If you add up the eigenvalues, it adds up to 1. And what's the entropy? Nope. 2. Log 2. Log 2. Log 2. It's 1/2 log of 1/2 plus log 1/2 log of 1/2. Altogether adds up to log of 1/2. Log of 1/2 is minus the log of 2, but we have a minus sign in the definition of the entropy. So it's log 2. That's the maximum that the entropy can be. I haven't stressed this, but it's an easy theorem. You might try to work that out. That the maximum the entropy ever can be is when all the elements of the density matrix are equal, maximum amount of ignorance. And so in this case here, we have a pure state for the combined system and complete ignorance for either of the components. For either of the spins. I concentrated on the left spin here, spin number 1, and what we found is that the density matrix described complete ignorance. In this case, what is the expectation value of the components of the spin, in particular spin number 1? All right. We could calculate them by using the full wave function here, or we can calculate them using the density matrix. The density matrix for spin number 1, rho, is equal to 1/2 times the unit matrix. We can just call it 1/2. It's just 1/2 times the unit matrix. The expectation value of any component of spin along any axis, is equal to the trace of rho times, just sigma dot n. Sigma dot n, trace of rho, sigma dot n, that's the average of sigma dot n. Trace of rho times the observable, that is not trace of rho, not the observable times trace of rho, but trace of the product of rho times the observable. That's the average of the observable. Well, rho is proportional to the unit matrix. You can take that out. Unit matrix doesn't do anything. It just gives you a half, factor of a half. Just gives you a half times the trace of sigma dot n. What's the trace of sigma dot n? Anybody know? 0. The trace of every one of the sigma matrices is 0. Let's just check that. Trace of sigma 3 is 1 minus 1. Its trace is 0. The others are all off diagonal. They also have no trace. So what have we learned? We've learned that in the singlet state, something we already knew because we'd already worked it out, that in the singlet state, the trace of every component of spin in any direction is 0, which means in any direction whatever, the spin is equally likely to be along that direction or opposite to that direction. We already knew this, and this was an example of a highly entangled state. We also know that for no pure state of a single spin is the average of the spin equal to 0 in every direction. So this is another way of seeing that, that this cannot be a pure state. But the easy way to see that it's not a pure state is that the two eigenvalues here are both non-zero. So it has to be a mixed state. So the singlet state is a maximally mixed state. Let me take another one. let's try the following. Let's see, up, I think I want 1 over square root of 2 here. Let me just, or do I want 1/2? Wait. I think I want 1/2. Yeah. Yeah, sure I do. 1/2 and 1/2. Yeah, now it's normalized, right? I have 4 psi star psi would give a quarter plus a quarter plus a quarter plus a quarter, no minus, plus, would give 1. So this is a normalized state with all entries equal to 1/2. Let's recalculate what we would get here if we had this situation. This is not the singlet state. All right, so now what do we have? We have up equals 1/2. So this is a quarter, right? Is that right? Right. And this is also a quarter. Quarter plus a quarter is again 1/2. No difference. All right, so this is still a 1/2. This one is still a 1/2, but so is this one. All the matrix elements are equal to 1/2. So it's 1/2 times 1/2 plus 1/2 times 1/2. They're all equal to 1/2 this time. And in fact, this one is also equal to 1/2. Now, this is the density matrix. Its trace is still equal to 1. That's good. Sums of the probabilities are equal to 1. But what are the 2 eigenvalues of this matrix? Are they equal? No, actually they're not. Let me show you what the 2 eigenvalues are. Let's calculate the 2 eigenvalues. Incidentally, do you know the theorem that says that the product of the eigenvalues of a matrix is equal to its determinant? That's one way to check the eigenvalues here. Good. Let's use that fact. This is a fact. The product of the eigenvalues of a matrix is equal to its determinant, and the sum of the eigenvalues is equal to its trace. So we now know the sum of the 2 eigenvalues of this matrix are equal to 1. That's good. The sum of the eigenvalues is equal to 1. What about the determinant of rho? Right. It's 1/2 times 1/2 minus 1/2 times 1/2. So the product of the eigenvalues adds up to 0. That means one of the eigenvalues is 0 and one of the eigenvalues is 1. Okay. What's that? Yeah, this is a product state. This is a product state. Can anybody guess what it corresponds to?
Right? 2 electrons.
It's what?
2 unentangled electrons.
It's 2 unentangled electrons, but what are the individual electrons doing? Yeah, they happen to be measured the same way, but which direction? In what direction? Along what axis?
Z up.
X. Okay. Let's calculate the expectation value of, let's start with the expectation value of sigma z. Let's start with sigma 3. All right, so for that we take the trace of rho times sigma 3. Let's see what we get. Sigma 3, and it doesn't matter which order. Sigma 3 is 1 minus 1, 0, 0. And rho is 1/2, 1/2, 1/2, 1/2. Okay, let's see what the product is. 1 times 1/2 plus 0 times this is equal to 1/2. 1 times 1/2 is 1/2, 0 times 1/2 is 1/2. And now minus 1/2, minus 1/2. Now I have to take the trace of it. Trace is 0. So the expectation value of sigma 3 is again 0. The same will be true of sigma 2, but let's calculate the trace of the product rho times sigma 1 now. Let's put sigma 1 there and see what we get. Sigma 1 was the matrix 1, 0, 1, 1, 0, 0. Okay, so on the top row times the first column, we get a half. Same thing over here. Looks like we get a half here also. Now we get, same thing. Everybody's a half, right? And the trace is equal to 1. So the expectation value of sigma 1 is 1. The expectation value of the other sigmas is 0. This is a spin. This is a pair of spins that happen to both be lying along the x-axis. It's a product. Its entropy is 0 because it has one 0 eigenvalue and one eigenvalue equal to 1. All right? So if somebody gave you this density matrix here and said, tell me, is it a pure state? All you have to do is calculate its eigenvalues and calculate its entropy. Or if they asked you, how pure is it? You could characterize it by its entropy. In this case, the entropy is 0. If you change these numbers a little bit, for example, make this, instead of 1/2, make it 0.4, and make this one 0.4 or something like that, you'll change things a little bit, and instead of finding a 0 entropy density matrix, it will have a small amount of entropy. In other words, there'll be a small degree of entanglement. So entropy, entanglement go together. And it's sometimes called, the entropy that one gets this way because systems are entangled is called entanglement entropy. Okay, let's take a little break. First of all, in the cases which we've been doing, we've assumed that the combined system is in a pure state. The combined composite system has a definite wave function. That means the combined system should be thought of as having a pure state. As far as the combined system goes, that means that its entropy is 0. There's no uncertainty in the wave function or in the state vector of the combined system. It has 0 entropy. The entropy that we're talking about now is the entropy of the subsystem. The subsystem now, which we're looking at, which is subsystem A. By virtue of the fact that it's entangled with B, A has an entropy. If you didn't look at B, A has an entropy. Notice one thing, and this is a general property of this kind of entanglement entropy, or this kind of entropy. It doesn't add. The combined system has 0 entropy. The two subsystems each have, as a matter of fact, would have entropy of logarithm of 2 in the singlet state. All right? So entropy in general does not add. So under special circumstances it may add, but in general entropy is not an additive quantity. In particular, entanglement entropy is not an additive thing, because the typical situation will be that the combined system is a pure state, 0 entropy. The two subsystems each will have some positive entropy. Okay. So we have to distinguish between the entropy of the subsystem and the entropy of the composite system. And as I said, I'll say it once more, it is not additive.
Sort of a first statement, you mentioned entanglement entropy, but all the entropy that you would find in quantum mechanics is all entanglement entropy?
I think it's probably fair to say it really is always entanglement entropy, but sometimes it's a little bit obscure what's entangled with what. But, you know, if you count the magnets and the people who prepared the system and so forth, then the only reason there would be for not knowing which way a spin was prepared would be that the preparation was entangled with the thoughts of the preparer or something. But if we want to keep the observer out of it, we would just say that that there's different probabilities. That's one origin of of a density matrix. But the other origin is entanglement. I suspect probably entanglement covers them all, but then you would have to think about entanglement with what, and it can get complicated. All right, I want to leave the subject of entanglement for a while. I'm pretty sure we'll come back to it. But there's one thing we haven't talked about at all. It's how states change with time. In classical physics, in classical logic, and if we're dealing with a discrete system, with a set of, with the configuration space being a system of points, could be just 2 points, heads or tails, the only kind of evolution that makes sense is discrete evolution, where time occurs in steps, and at each step the system moves from one state vector to, not state vector, from one configuration to another configuration. And you could simply represent the evolution by a permutation. If you start in this vector, sorry, I keep saying vector. If you start with this state, you go to here, you might go to here, you go to here, you go to here, 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 and perhaps back to here. That would define the evolution of a system. Just a permutation which tells you where every state goes. It doesn't have to be all connected like this. You could have 4 states, and the rule could be this one goes to this one, this one goes to this one, this one goes to this one, this one goes to this one. That's also okay.
Why it has to be discrete time?
Well, because how are you going to go from one discrete state to another discrete state continuously? How are you going to go from heads to tails? Well, you could turn it over slowly, but no, but that would mean that there were intermediate configurations. That wouldn't really be a 2 configuration system.
You're talking about discrete configurations.
If there are discrete configurations, then I think you would have to say that that evolution would occur in discrete steps. Right. In quantum mechanics, in some sense, you can have, well, we certainly have systems which are discrete, a finite number of orthonormal states, but the evolution of a system can be continuous. Now, why is that? You can have, well, why is that? You can continuously go from up to down. Up means a magnetic field pointing along the up axis has locked the electron into place. Down means the electron has been locked into place by a down magnet. And of course, you have an infinite continuous number of possibilities in between. So although there's only 2 measurable possibilities for the upspin, so in that sense, the system is discrete, nevertheless, you can continuously interpolate between them, and so that allows the possibility then that state vectors can vary continuously with time, even for a system which is discrete in the sense that the dimension of the vector space is finite. Let's talk about how state vectors change with time. Now, there's an assumption. And the assumption, the basic assumption, is that the logical relationships between states doesn't change with time. For example, if you start with 2 states which are the same state, then, and allow the system to evolve, of course, the 2 states will evolve into the same state. That's trivial. You start with a particular state and you let it evolve. It evolves into some definite state. What about if there are 2 states of the system which are orthogonal to each other? Spin up and spin down. Well, the assumption is that 2 orthogonal states of the same system, if you allowed them to evolve, would evolve into 2 orthogonal states. That the distinctions, the fact that they're measurably different, will be preserved with time. You could imagine, incidentally, that's also true in the classical description, that you don't have the situation where 2 different states could evolve to the same state. that never happens in classical physics. You would lose memory then, and then maybe you go to here. Starting here, you could go to here, and maybe from here you go back to here. Well, then you would lose memory of whether you started here or here, because whether you start here or here, you wind up here. That doesn't happen in classical physics. There's never a loss of memory of where, yeah.
So I was thinking bifurcation or nonlinear analysis, essentially you do have multiple steady states.
Not at the microscopic level. Not at the microscopic level. Right. This is a principle of physics. In classical physics, it's called conservation of phase space volume, that the phase space volume stays the same, never contracts or expands. But in quantum mechanics, it has another name. The other name is unitarity. But what it says is that the inner products between two states stay the same with time. If two things are orthogonal, they will remain orthogonal. Each state will change in its own way, but if state number one is and state number two are allowed to evolve with time, they will remain orthogonal. So, for example, if you start with a spin up and you put it into some magnetic field that could be doing complicated things, after a while the state will change with time. If you started with a state down, after a while it will change and become some other state, but the two final states will remain orthogonal to each other. All right, so the principle...
Is that only if they're under exactly the same influence, though, right?
Yeah. Under the same influence, right. Yes, absolutely. Yeah.
Well, this may seem obvious, but so if one spins up, one spins down on the z-axis, and we put it to a magnetic field, the line along the x-axis,
Yeah.
we continue to be orthogonal.
Yeah, what'll happen is if you put it into a magnetic field along the x-axis, and you start with either a spin up or down, they will begin to precess, they will rotate. All right? So they might rotate after half a period or something to one being along this axis, the other being along this axis. But those are orthogonal to each other. Okay? So orthogonality is maintained with time. Even stronger, inner product inner product between two vectors is time independent. So let's actually, I should say that's the second principle of time evolution. The first principle of time evolution is that it's governed by a linear operator. Let's start with the first principle first. Start with any state psi. It could be any state of the system. And let's imagine it at time 0. Okay. After a certain amount of time, it evolves to a new state, which is the state at time t. The principle of quantum mechanics that I'm going to say now is, first of all, that the evolution is linear. This can be summarized very easily by saying that psi of t is always equal to some linear operator. I'm going to call it u, which is a function of time times psi of 0. What is u of time t equals 0? What is u of 0? 1. The state psi at time 0 is just equal to the state at psi at time equal to 0. So whatever u is, it's equal to 1 when t is equal to 0. But at some later time, the state vector is changed, and the assumption. Now, this is, again, one of these things which is justified by its empirical success. Right? It's justified by its empirical success. But you will see as we go along how this connects to other things in physics and why it might be, how we know this is true. But let's just take it as an assumption that there exists a linear operator which is dependent on time. It's not just a fixed linear operator. It evolves with time, and whatever the state is at time 0, you hit it with u of t to find out what it's doing at a later time. That's the first principle of time evolution. The second principle of time evolution is that if we have two vectors, and now I'm writing a bra and a ket, and we allow them to evolve with time, both of them, that the inner product between them is unchanged with time. In other words, that it's equal to phi of 0 times psi of 0 for any value of the time. This is the statement that distinctions between states are maintained with time if they're orthogonal. It's enough actually just to know that orthogonal states go to orthogonal states. From that you can prove that inner products remain invariant. But in particular, for example, if phi and psi are the same, then this is just a normalization. Phi is just a normalization, which we normally set equal to 1. This is just a statement then, if phi is equal to psi, it's just a statement that the total probability doesn't change with time, that the normalization of the state doesn't change with time. On the other hand, if phi is orthogonal to psi, then what it says is that psi and phi are measurably different. There's an experiment that you can do to distinguish them uniquely, and that will be true either at time, if it's true at time t equals 0, it will continue to be true at a later time. So the logical relations between states stay invariant with time. That's an assumption, of course, but it is true. All right, let's see what this condition here, and this is true for any pair of vectors psi and phi. Let's see what it says about u. Okay, psi is equal to u of t times psi, but let's look at the bra vector. What about the bra vector? Shall I write u here? U dagger. The Hermitian conjugate. Remember, when you Hermitian conjugate or when you complex conjugate an expression, you'll have to put in the Hermitian conjugate here. All right, now let's see what happens to phi times psi. This is equal, well, it's equal on the one hand to phi of 0 u dagger, u times psi of 0. But it's also equal to just phi of 0 psi of 0. And this is presumed to be true for every vector, every pair of vectors psi of 0 and phi of 0. Well, if an equation, I won't prove this, this is more or less obvious. If an equation like this is true for every vector, every pair of vectors in the vector space, there's only one conclusion, and that conclusion is that u dagger u must be the unit operator. Okay, that's something easy to prove, very easy to prove. I'll leave it to you to prove that if there's an operator whose matrix element between any pair of states is the same as just the inner product between those states, it follows that operator must be the unit matrix. So here's what we learn. We learn that u dagger u is equal to 1. Matrices with this property, or operators with this property, that the product of them times their Hermitian conjugate. First of all, before we even talk about that, if these were just numbers, it would correspond to a number times its complex conjugate. If a number times its complex conjugate is 1, what does that say about the number?
Unit vector, or radius 1.
It's a phase. It's a pure phase. It's an e to the I theta of some sort. On the complex plane, it says that it's on the unit circle. It's unit in length. Right? It's if u dagger u is equal to 1, if it were a number. Matrices with this property are called unitary. So one would say that the time evolution of quantum systems is governed by unitary operators which depend on time. Let's imagine a very small time interval, a time interval of magnitude epsilon, where epsilon is a very small number, so small that we can ignore the square of epsilon. In other words, in our equations, we're going to retain things just the first order in epsilon. And let's see what it says for a matrix to be unitary. All right, first of all, if t is equal to 0, in other words, if epsilon is equal to 0, epsilon is a little interval of time, if epsilon is equal to 0, then u is equal to 1. So let's write down u of epsilon, epsilon is a small interval of time, starts out being 1, and then there's some small correction to it, and that correction is of order epsilon. Let's assume it's of order epsilon times some operator, which is the first order correction. All right, now I am going to, just to avoid changing definitions in midstream, I'm going to put a minus sign here, but that's purely a definition. I'm going to call the operator here h, and I'm also going to put an I here. This I so far has no special meaning. It's arbitrary. I could absorb it into the h if I liked, and I could also absorb the minus sign in, and I could have just written 1 minus epsilon h, but for later purposes I know that I'm going to want to define h so that there's an I here and a minus sign. The minus sign is completely arbitrary. The I is a nice definition, as we'll see. So let's see what the condition on h is for u to be unitary. Let's write it down. U dagger u, oh, what is u dagger? U dagger of epsilon is equal to 1 plus I epsilon. Remember, we have to complex conjugate everything when we take Hermitian conjugate. And then we have to write the Hermitian conjugate of h. The Hermitian conjugate of 1 is just 1. The Hermitian, the complex conjugate of I epsilon is minus I epsilon, so the sign changes here, and we substitute for h, we substitute h dagger. And now we multiply the two of them, and eventually use the approximation that we can ignore epsilon squared and only keep things to order epsilon. All right, so the product is 1 plus I epsilon h dagger times 1 minus I epsilon h. What does that have to equal? Well, if u is unitary, that has to equal 1. So let's expand it out. 1, now we have 1 times minus I epsilon h, minus I epsilon h, and then we have plus I epsilon h dagger, and then we have something of order epsilon squared. Okay. All of that has to equal 1, and we're going to ignore epsilon squared. Epsilon is so small that we can ignore it. We don't want to ignore epsilon, the reason being that the 1's cancel on both sides. Okay? The 1's cancel on both sides, and so the leading term is proportional to epsilon. And what do we get? We get I epsilon h dagger minus h should be equal to 0. Or in other words, the leading order in epsilon h dagger, the conclusion is that h dagger equals h. In other words, h is Hermitian. H has a name. It's called the Hamiltonian. It's Hermitian, so it's an observable, and the observable that it corresponds to is the energy of a system. The eigenvalues of the matrix H are the energy levels of a system. Right? But this was the main point, that defined in this way with the I here, H should be Hermitian. We can write this another way. Let's write it another way, the following way. Let's write psi of epsilon minus psi of 0. What is that? Right. Psi of epsilon is 1 minus I epsilon h times psi of 0 minus psi of 0. Well, that just means the 1's cancel. Psi of epsilon minus psi of 0 is just equal to minus I epsilon h psi. It's just the difference between them, the extra little piece in u that comes from here. This is a difference, but let me divide it now by epsilon. Divide everything, both sides of the equation, by epsilon. Well, this looks like the derivative of psi. Well, now let epsilon be very small. Take the limit that epsilon is very small now. This is the difference of something at epsilon and at 0 divided by epsilon. This is the derivative of psi with respect to epsilon, or with respect to t. Epsilon is just a small interval of time. Right? So the change in epsilon divided by a small interval of time, that's the derivative of the state vector with respect to time, is equal to minus I h on psi. This tells you how the wave function of a system, or how the state vector of a system, I should say, how it changes with time. H being Hermitian guarantees that U is unitary. If it's unitary, it guarantees that the logical relations between states are maintained with time. And this is the equation which governs the evolution of every quantum system. Of course, you may get to pick what H is. I haven't told you what H is. H may depend on a particular setup. For example, H may depend on the magnitude of a magnetic field. It could depend on all kinds of things. The only thing we learn from general principles is that the Hamiltonian should be a Hermitian operator. A Hermitian operator has eigenvalues and eigenvectors, and the eigenvalues are called the energy levels. Okay. So this is the way a state vector changes with time. In principle, H can be a function of time. For example, if you have an electron in a magnetic field and you change the magnetic field. But if you have a situation where nothing is changing, magnetic field or whatever it happens that's governing the system happens to be time independent, under that circumstance, H is simply a fixed, definite matrix, a fixed, definite operator that is called the Hamiltonian. Any questions?
So far, can I conclude that if two things are entangled, they're going to stay entangled?
Not really, no. No. The only way, no. No, the only thing you can conclude is if you have two different state vectors, the inner product of them remains invariant with time. Now that's not, doesn't tell you that entanglement, no, that is not correct, the two things. If it were correct, you would not be able to entangle one thing with another. If they were unentangled, they would remain unentangled. And measurements could not be done. Right. So no, that does not follow.
Well then, do we have a unit for entanglement? Some way of...
Yeah, the entropy.
That is the...
That's the unit of entanglement.
And that's joules.
Is what?
Joules.
No. Oh, no. Entropy, okay. Entropy is a pure number.
It's a state description. It describes the set relationships, and it has no...
No dimensions. No dimensions. It's measured in bits. It's measured in bits, but bits are measured in units of log 2 or something. Right. No, okay. Yeah. All right, so let's go through units. The standard thermodynamic units. For standard thermodynamics, let's write the thermodynamic equation. Here's a thermodynamic equation. The differential change in the energy and the heat of a system is the temperature times ds, but let's see, we usually put a k in there or not? No k in there, right? No. Now, what are the units of temperature? Well, okay, degrees usually, but let's write another equation. Another equation would be the fact that the kinetic energy of a particle in a gas is 3/2 K, which is Boltzmann's constant, times the temperature. So the temperature always has units of energy. Temperature has units of energy divided by Boltzmann's constant, whatever the units of Boltzmann's constant are. I mean, the units of Boltzmann's constant are energy divided by temperature. All right. But you know, the only reason that there was this stupid Boltzmann constant in physics is because people measured temperature with a stupid thermometer that they bought in a hardware store. Okay. The natural real units for temperature are energy. Get rid of the Boltzmann constant. It's just a conversion factor from units of energy to units of Celsius or whatever. Once you just get rid of the Boltzmann constant and say temperature is measured in units of energy, then energy, dimensionless. Entropy becomes dimensionless, and entropy, why is it dimensionless? It's the logarithm of an integer. How could it have dimensions? Of course, you assign it the dimensions of bits, but a bit is just meaning a unit, a dimensionless unit. So entropy is dimensionless unless you want to put back the Boltzmann constant, and then where does it go? I can't figure out where it goes.
Then it's energy per temperature.
It's energy divided by temperature in either case, but yeah. But for our purposes, we want to define entropy in an information theoretic way, and all information theorists would call entropy absolutely dimensionless. It's only when they want to connect it to thermodynamics and then use for the unit of temperature a thermometer that Boltzmann's constant enters into the story. Good. You know, I don't think Boltzmann ever knew his own constant, incidentally. It wasn't until Einstein in 1905 that Boltzmann's constant was actually measured. Einstein figured it out, how to measure it. And Boltzmann committed suicide the year before because he was very discouraged because nobody knew what his constant was. It's one of the real sad stories of physics. I shouldn't make fun of Boltzmann. He was a very great physicist. Where are we? Yeah, I'll tell you what. I'm going to jump. I was going to talk about the eigenvalues of H, but I'll do that next time. And they are, of course, just called the energies, the energy levels.
Will you tell us why the relationship H is related to energy? Or?
It's just called that. Why? Because it's conserved. Okay, let's. All right, it goes back to Einstein. Well, everything goes back to Einstein. That doesn't say anything. Okay. You know that the way the wave function varies with time is with an exponential phase that depends on energies, and that's E equals h nu, right? Oh, there should be a Planck's constant in here if I really want to keep track of where does the Planck's constant go here?
I think the
No, the other side. The other side, right? There's a Planck's constant here, so let's put the Planck's constant there.
I think there's 2 pi usually in there someplace.
No, there's no 2 pi in there. The 2 pi is depending on whether you use H or H bar, and with H bar, there's no 2 pi in there.
No, it's H bar I on
What's that?
the, H bar I on the right, left-hand side, so it can be.
So,
Wait, let me see.
Are you saying it's over H bar? That makes sense.
Yeah. Yeah.
Ah, yes, it's over, sorry, d by dt, yeah, it's over H bar. Over H bar. Yeah. Yeah, energy levels are very small things in quantum mechanics, and you divide by H bar to find out how the system changes with time. Okay, good. Let's suppose that psi is an eigenvector of H. H on psi is equal, well, let me call it omega. If it comes out to really be omega, I'll be very happy. Let's call it omega on psi. Omega being, no, energy, E, energy, E for energy. E is a number, psi is an eigenvector of H with eigenvalue E, okay? Just assume. That means I'm getting tired, I'm beginning to fade. If psi is initially an eigenvector of energy, it will remain an eigenvector of energy for all time. Let's see if we can solve this equation. Let's see if we can solve this equation, assuming that psi remains an eigenvector of the energy for all time. Okay. Now, if it remains an eigenvector of the energy for all time, you say, wait a minute, that means it doesn't change. If it doesn't change, this is nonsense. No. Psi is an eigenvector, but remember that you can multiply an eigenvector by a number, in particular a complex number, and it still remains an eigenvector. So let's write that psi of t is equal to a function of time times psi of 0. If psi of 0 is an eigenvector of the energy, so will f of t times psi be an eigenvector of energy, and therefore so will the left-hand side. It'll be the eigenvector with the same eigenvalue. It'll just be multiplied. And let's see if we can solve this by seeing if we can find an f of t which will allow this to be solved. Okay, so what does it say? We just factor out psi of 0, and what it says is that the f of t by dt is equal to minus I. Now, h on psi gives E times psi. So that gives an E divided by h bar times f, all multiplying the vector psi. But we can divide, we can just get rid of the vector psi at time t equals 0. This equation just becomes an equation for the function f of t. The f by dt is minus I E over h bar f. all I've done is substitute for psi of t, f of t times psi of 0, and then use that h on psi over here is e times psi. You know how to solve this? The solution of an equation like this is just that f goes like e to the minus I e over h bar t times f of 0. So what it says is if you start with an eigenvector of the energy or eigenvector of the Hamiltonian, then it evolves with time just by multiplying by a time-dependent phase. That's all that happens. Okay? What do you call a coefficient in an e to the I something t? What do you call a coefficient of t? Well, no, it's usually called a time constant if it's real. Then it would be the decay constant. You call it the frequency. You call it not the frequency, but the angular frequency, omega. So we have that the wave function evolves with a frequency, with an angular frequency, omega, which is equal to the energy over h bar, or better yet, energy is h bar times omega. That should be a familiar equation. It also can be written energy is ordinary frequency times Planck's original constant. Differs by factor of 2 pi. I'm getting tired and my cold is getting worse and worse, so we're going to quit now. But I thought I would just show you this and we'll come back to it. But the phases and the fact that frequency is related to energy is equivalent to this equation, which tells you how states change with time. This equation also has a name. The name is the Schrodinger equation. This is the Schrodinger equation. It's not the particular Schrodinger equation that Schrodinger wrote down for a particular free particle. That was a particle in a potential. That was a special case of this. This is the generalized Schrodinger equation for any system, but you have to pick a Hamiltonian. We'll do some of that next time. We'll pick out some examples. Again, particle in a magnetic field, or other examples like that.
The preceding program was brought to you by Stanford on iTunes U and is copyrighted by the Board of Trustees of the Leland Stanford Junior University. Please visit us at itunes.stanford.edu.